Hey, this is Max Nolito. I'm one of the electrical engineers.
Hi, I'm AJ, and I'm the systems engineering major.
Hey, I'm Andrew Layton. I'm one of the mechanical engineers on the project.
Hello, my name is Katie Shine, and I'm electrical and computer engineer.
Hi, I'm Graham Nellis, and I'm a mechanical engineer.
My name is Matthew Redondo, and I am the software major on the team.
Hi everybody, I'm Daniel, also known as Oni, and I'm the electrical engineer on the team.
We are the trash formers.
Moving heavy garbage cans isn't something most people think about until it's trash day. It's 110 degrees outside, the driveway is long and steep, and the bin is overloaded. For many homeowners, especially older adults or people with injuries, dragging a full garbage can up and down a driveway is inconvenient at best and unsafe at worst. Not to mention the added difficulties if the driveway is sloped. Our project tackles that specific problem. In this video, we present our autonomous garbage can tug system, a low-profile, robotic tug that attaches to a standard residential garbage can. It moves the garbage can from its storage location to the curb and back. While detecting and avoiding obstacles, it works seamlessly with standard garbage truck pickup routines. The goal is simple: make trash days safer, easier, and seamlessly integratable to current pickup routines. Our objectives were driven directly by stakeholder needs, homeowners, waste management crew, and our sponsor. At a high level, the system must reliably move a full can from a defined storage point to a curbside pickup location and back again, with minimal user interaction. To achieve that, we focused on several key requirements: safely traversing sloped and uneven driveways while towing fully loaded can, navigating along a repeatable path using GPS waypoints and onboard localization, detecting obstacles such as cars, people, or debris and stopping when found, maintaining compatibility with the standard off-the-shelf garbage can and a normal pickup truck, operating with a per-unit cost target of around $1,200 and within our overall project budget of $5,000, and finally, providing a simple user interface for scheduling runs and monitoring status. These objectives guided all of our design decisions from mechanical layout to control software. To move from the idea to working prototype, we followed a system engineering process. First, we performed stakeholder interviews and a risk analysis to identify the most crucial failure modes, such as the tug losing control on a steep driveway, failing to stop for an obstacle, or running out of power halfway to the curb. We then rate these risks and use them to prioritize design features and tests. We built several early prototypes to de-risk the hardest problems, a basic drive platform analysis to test tractive efforts on inclines, a mock-up towing arm to validate how forces transfer to the can, and early software tests for GPS waypoint tracking and vision-based obstacle detection.
All the individual pieces of work, now it's time for them all to come together.
One of the things that we had to consider when choosing our sensors was the environmental factors that they would have to endure. So, being in Tucson, Arizona, one of the biggest environmental factors that we think about is just the sun and the rain. So, one of the sensors that we were looking into were these sensors called ultrasonic sensors. And since we have so many bats in the area, we figured it would be a perfect sensor to use. However, when we were looking into those sensors, we ended up testing them and seeing that they were accurately choosing where the location of an object was, both being in motion, and it was very fast. However, when we went to test it in the wind was actually distorting the ultrasonic beams that were being put out from the sensor. And so because of that, we had to change the sensors to be radar, and those are very good at determining what the distance of an object is, no matter if there's rain or if there's wind, which are two very common factors in Tucson, Arizona.
Metal I got from work? Or?
I think we're still gonna need it, yeah.
Okay. I got it in the truck, so.
Okay, perfect. I think
To our sponsor, we are delivering a functional prototype of the autonomous garbage can tug, along with supporting documentation. This includes a user manual that explains system operation, charging, and basic troubleshooting in a clear, non-technical language, as well as a quick start guide for setup and scheduling the first run. We also provide technical documentation for future development, wiring diagrams, mechanical drawings, software architecture, and test reports. Together, these deliverables allow our sponsor to understand, operate, and further refine the system beyond our project timeline. As with most engineering projects, we encountered several surprises. One major lesson was how sensitive traction is on slopes when the can is heavily loaded and the surface is dusty or wet. Early tests revealed more wheel slip than expected, which led us to adjust tire selection, weight distribution, and control algorithms for acceleration and braking. We also learned that GPS alone is not perfectly precise at driveway scale, so we had to design our route and stopping logic with realistic error margins and rely on multiple cues rather than a single sensor. Another surprise was the importance of user experience. Small things, like how the tug attaches to the can or how clear the web app is, made a big difference in perceived usability, so we iterated on those details as much as on the core technology. Overall, these challenges pushed us to think more holistically about the system and the real-world use.